Welcome to this explainer. Look, if you've ever stared at physics formulas and felt totally lost in a sea of variables, trust me, you are not alone. Today, we're taking the exact mathematical relationship between electric fields and potential, and we're turning it into something you can actually visualize. We're stepping away from the dense textbooks to see the actual mechanics of the universe unfold right in front of us.
So here is our roadmap for today. We'll kick things off with 1. The familiar gravity analogy. Then 2. Natural versus forced motion. Next up, 3. Deriving the master equation. 4. Visualizing the potential gradient. And finally, 5. Summary and unit equivalence. Let's get right into it.
Section 1. The familiar gravity analogy.
Okay, notice how perfectly the physical world mirrors the electrical one here. If you look at that yellow arrow pointing down on the left, it's just pulling a regular mass downward, right? Now follow that pointing hand over to the cyan and red arrows on the right. Dropping a mass is beautifully and mathematically identical to dropping a positive charge in a uniform electric field. The formulas for work at the bottom, force times distance, are the exact same blueprint. We're literally just swapping out the variables.
Section 2. Natural versus forced motion.
So check out the red positive charge on the left. It's naturally moving downward with the blue electric field arrow. Because it's just going where it naturally wants to go, the field is doing positive work. Simple enough. But now, compare that to the right side. We have an external force, that yellow arrow pointing up, pushing against the field just to keep the charge in equilibrium. Because we're actively fighting the natural downward pull of the field, this requires negative work. It's exactly like lifting a heavy box straight up against gravity. And that brings us to the crucial point on this slide, that negative sign right smack in the middle of our equation. See the hand pointing out that the work from point A to point B equals negative Q0 times E times D? Why is that? Well, because that yellow external force arrow has to point directly opposite to the blue downward field arrow just to hold that charge steady. That little negative sign is literally just the mathematical translation of pushing something uphill.
Section 3. Deriving the master equation.
Okay, follow the glowing arrows flowing down the screen as we substitute that work equation we just found. Look at how the Q0s, our little test charges, perfectly cancel each other out on the top and bottom of that fraction. It's just mathematically elegant. It leaves us with this clean, super simple relationship where the potential difference equals negative E times D. And this brilliantly illustrates our core concept. By just shifting that distance variable, d, to the bottom of the other side, look at the highlighted text. Electric intensity, E, is simply the ratio of the potential difference over the distance between the plates. You literally just take the voltage drop, divide it by the distance, and remember to keep that highly important negative sign.
Now if we zoom in, like looking through a magnifying glass at an infinitesimally small distance, which we call delta R, moving directly along that field line gives us the absolute maximum rate of change. In math terms, this exact local steepness is called the potential gradient. It tells us exactly how intensely the voltage is dropping at that one specific microscopic point.
Section 4. Visualizing the potential gradient. Okay, this is the real aha moment. Trace that large blue vector arrow pointing straight down the glowing staircase. This is the perfect visualization of how the electric field equals the negative gradient of potential. All that really means is that the electric field always points down the hill. It flows directly from the red high potential plateau straight down to the blue low potential floor. The electric field always points in the direction of decreasing potential. Really let this core rule sink in for a second. Because that negative sign in our master equation, it isn't just some weird math quirk designed to make textbook problems harder. It is a fundamental physical law. It dictates that electric fields are perpetually pushing towards lower energy states. It's the invisible architecture of the universe trying to find balance.
Section 5. Summary and unit equivalence. To prove this, follow the red slash striking right through the screen, canceling out meters on the top and bottom of this fraction. This dimensional analysis definitively proves that measuring a voltage drop over a distance, which we call volts per meter, is mathematically exactly identical to measuring physical force per unit of charge. The math perfectly validates the physical analogy we started with.
So whether you're in a lab saying 1 volt per meter or 1 Newton per coulomb, you're describing the exact same physical reality. They are two sides of the same coin. One phrase describes the steepness of the potential hill, and the other describes the physical force you'd feel rolling down it.
As we look at this master summary grid, follow the arrows from the core concept on the top left all the way to the master equation on the top right.
We've successfully walked from a simple gravity analogy through the derivations to proving the fundamental structure of electric intensity. We visually verified it, mathematically derived it, and dimensionally proved it.
So what does this all mean for you? Well, now that you can visualize these invisible gradients pushing charges down a physical staircase of potential, consider this. Manipulating these very hills and valleys is exactly what powers every single electronic device in your life. Your phone battery? It is literally just a portable potential gradient waiting for you to complete the circuit. And on a much grander scale, these same invisible hills and valleys are what unleash massive lightning strikes in a thunderstorm. So the next time you plug in your phone or see a flash of lightning across the sky, ask yourself, how are these invisible gradients shaping the world around you? Thanks for joining me for this explainer. Keep visualizing the world and stay curious.